Thank you. So, yes, as I said, my name is Kresten, and I'm CTO of Trifork. I've been with Trifork, or CTO of Humio. I'm some used to say I'm CTO of Trifork, but I've been that for 20 years. So about a year ago, we started out with Humio and going full time into it actually since January. So we just launched our product almost 5-6 weeks ago. We've been working on it since January. So this is one of the first. I've been doing the rounds at the GOTOs this fall and other conferences, introducing this product. So just briefly, the agenda for today is just a little bit on who we are and why I'm here, and then I'd like to start out with just a super quick demo, just 5 minutes of demo time to just show you what this product is and why, just to give some context of the rest of the talk. And then the major parts are why we're doing this and how it works. And then if there's time in the end, we'll have more examples or questions and stuff from the audience. So, as I said, we're Humio. We're Meet Humio at Twitter. There's Gita, me, and Christian as the core team. We are actually 6 people total working on it. The other ones have been consultants up till now. Gita is the CTO. She has been running the GOTO conferences. She's been global manager of GOTO conferences for the last 10 years. Came from Sun Microsystems as a product marketing manager before that. I've been CTO in Trifork for the last 20 years. Christian actually started out his career at Trifork and then spent some years at Xamarin and came back for this project. So this was from Copenhagen, the day we launched the product in, I think, 3rd of October or something like that. So it's only 5 weeks this product has been in the wild. So let me start by showing you just really briefly what this is about. And I have a demo set up here where we're taking the live event stream from GitHub. So this is all the events that happen on public repos at GitHub. And so this is like every time you push to GitHub, every time you comment something on GitHub, every time anything happens, every time you like something on GitHub. There's this event stream that you can subscribe to, and it's really nice to have some live data to show. So the tool itself looks like this. If we go into the GitHub data space here, where we pulled in the event stream from GitHub, and each of these lines of logs here is a JSON structure that looks like this. In this case, it's nice structured JSON. We can also take any other kinds of logs, but JSON is so nice because you just say it's JSON, and then it's fairly easy to parse. So each of these have a type, as you'll see at the bottom. This is a watch event. Somebody clicks the like button eventually on GitHub. So let's say I want to see all the watch events. So now I get filter. Across here you see a kind of a graph of how many of these happen over time. And then the idea in the tool is it works kind of like you can think of it as a grep on steroids. It works like a Unix command line pipe sequence, where you could do stuff like, normally you would do sort, unique, count, grep, etc. Here we do stuff like group by. For instance, I want to group by the repository name, and I want to sort that. So here we get repositories looking over the last, in this case, 24 hours, that had the most likes on GitHub. Right, so this could apparently Palantir just released something, and this is a UI toolkit. This is the first open source thing from Palantir. So we could do this over 24 hours, or we could do it over a longer period of time here, going back. So you can see the search runs kind of backwards over the last month. The GitHub repos that had the most likes. So this is running, this demo machine is just running, it's a single 4-core machine with standard disks that we run this on. And this, even though you see it kind of going fairly slowly backwards, it's actually fairly fast if you compare it to other stuff. So that's one part. You can also take this query and say, this pipeline, just keep it running. I want to keep this running on new events as they come in. So that's more easy to understand, easy to see if we look at a shorter time frame here. So here we look at a real-time stream of the last 5 minutes, which repositories have been getting the most likes here. So if we limit this to some smaller number, say we want 7, the 7 repositories that have the most, we have different visualizations. You can see it as a pie chart and what things. You can take these things, and so these visualizations, like this, put them into a little dashboard. So here's a GitHub dashboard that shows some things about what's going on at GitHub right now. So these live queries are real event processing capability in the system that doesn't really add any significant load to the system. So you don't need to run the entire query again every time you show this. Anyway, so that was a really brief demo. Let's go back to the talk. I'll give you some context for it. So the why in this is that we have been, we come out of Trifork. We come out of a large consulting shop where we do all kinds of systems, and we've been doing that for many, many years. And most importantly, about 10 years ago, we started building 24/7 systems. And most of these most interesting systems are really composed of many servers and services. Today, it's the microservices, cloud distributed systems. These things have different names over time. But really, when you look at these, logs is really a time-proven lowest common denominator to understand what's going on in these systems. Back in the days of J2E, everything ran on one app server. It was very easy to go in and look at the log, D-log for the system, because everything was running on one machine. But nowadays, it's really split out over many machines, obviously. And having these logs together is really key to understanding this. So we've learned this over time. In the last 10 years, one of the large systems we built was this Danish equivalent of the British NHS Spine. It's a large healthcare infrastructure for anything to do with drugs, prescriptions, etc. And that was, of course, very important to have high availability and high security requirements. And today it runs on a good chunk of servers and many different services, and has many different external connected systems. So in this process of building this, you need to have, it's really difficult to see into the system. What is the health of the system? How does it feel like? So what you want to do is build some notion of what's normal. How does the system behave when it's normal? So the human brain is really good at this, right? We sense what's going on outside, and it translates into a sense of normal. But what does this normal mean for an IT system? And what you want to do is have some kind of dashboard. That's a really good experience we had, is set up dashboards, and we have these dashboards in the developers' offices everywhere, where the systems they're responsible for, they have these dashboards, and it's not because they necessarily need to make that much concrete sense as they are, but they're there, and you can sense when you kind of internalize what's the normal behavior, because it's just always sitting there. It's very boring. There's these graphs sitting there, but when all of a sudden it behaves differently, that's where it's interesting. and putting this human brain power to good work when this happens is super valuable. So assume you, in a healthcare system like our drug system, right, over the course of a day, we might have a graph that looks like this. So this is how many, assume maybe it's the number of prescriptions that are issued over the day. You can see the lunch break in the middle when everybody goes to lunch break. And it could be that when you overlay several days of these, it's very easy to see that, yeah, this looks kind of normal, even though it's slightly different. But then all of a sudden, something like this happens, and you can go, and then you have to react, right? You can, this could be the day after Christmas or the day after Easter, when everybody kind of kept their illness to themselves for a few days, and everybody had to go to the doctor Monday morning, the first day after the vacation. This is typical behavior. So you learn that. But having this sense of normal directly in the development environment and being able to interact with your data is super valuable for just feeling confident that the system works. So another aspect of running a system like this is, because of the high security requirements, we really, as developers, couldn't access the systems at all. I mean, everything was literally throw it over a wall. We had smart people on the ops side, but because of the security requirements with these healthcare systems, developers couldn't interact with the production systems at all, only by a ticketing system. So everything was described and through a ticketing system, so the ops guys would have to do so and so. This wasn't anything we could do about. But by actually exposing the logs of the system in a structured and organized way, it did give us some insight into when things happen in production. Having a read-only access to this could be permitted, given that we had full audit logs of which logs were accessed. So that's really a way to provide visibility into a production environment in a high security environment. Another thing that happens as soon as you get access to these logs is you want to be able to iterate on how you access them. So often I see in organizations they set up a dashboard and they show like the performance figures or the KPIs. There's a special team, an ops team, that goes off and create these dashboards, and then they're pretty much fixed. You look at them, but you never interact with them or change them or build your own. So we found if you have a system where developers can go and create their own dashboards and do their own special measurements, and also easily be able to add stuff to the measurements that are shown. So maybe for a new subsystem as part of a larger architecture change or whatnot, easily be able to add things. So also in terms of logging and measuring, make it really easy to turn this crank of iteration of how you get insights into the system. We found with many systems that it's really difficult to do this, being able to iterate on what you see in the system and how you get insights into how the system works. So another issue is you want to be able to take many different kinds of logs. In our case, this healthcare system was built on these kinds of technologies and others, and it's really valuable to be able to take logs because they're so. As I started out saying, these are lowest common denominator, really easily accessible. Everybody, if it's part of your software that you control, it's very easy to add extra information to the logs. If it's part of the system that you don't control, such as maybe you're not committer on MySQL, so you can't really change the logs on MySQL, but you can grab the logs because they're text, and you can easily take information out of them and show it on a graph like this. So there's many different requirements that kind of all add up to what is a log aggregation tool. So I still, as you know, in my from Trifork side, we still see lots of projects that don't do log aggregation. This is seen as, this is a luxury that you can add if the system gets too big or too complex, but it really gives you a very easy and low resistance impact, low resistance insight into what the system does. And as soon as you're onto it, you get totally hooked. It's like crack for programmers. You get you need this insight as soon as you're used to it. And this is kind of, I know we're not obviously we're not the only log aggregation advocate out there, but this whole thing of aggregating logs and taking information out of them is kind of like test-driven programming. In the beginning, when the guys were running around advocating test-driven programming, everybody was like, yeah, but how do we derive the value out of that, and is it really worth it? And now you're kind of stupid if you don't do enough testing up front. I think this is quite obvious, something that will bring a lot of value into any size project, that you get insights into what the system is doing. So this is something you can go home and advocate to your organization or to new projects you're engaged in. So our particular engine is, of course, built on these experiences and others. We have used various log aggregation tools. In particular, we've been using Splunk quite extensively, and we've used the Elk stack quite extensively. And what we wanted to achieve was really, you may imagine you're standing in a consulting shop that does lots of consulting projects for various size customers. Some are big enterprisey ones that would want to pay for the enterprise solution. Some are smaller ones that just need something simple and easy. So what really we wanted to achieve is build something that was both fast and flexible, affordable to put in projects, simple to install and use, or just really something that we'd like to use ourselves. So at the core of Humio, what it is, kind of from a technical point of view, you can think of it as a very simple time series text database. So it's a time series database where every record is just a timestamp and some text. And then it has these properties. It's an in-memory stream processing system. Lots of these high-frequency trading systems are using this kind of notion. We support these live queries or standing queries. We don't do term indexing, so we don't build up large indexes. Instead, we just compress the storage, and we're really clever about how we then process the data. And we have various APIs that I'll talk a bit about later. So, assuming we have some data put into the system, how do you get them out? So the query mechanism, as I showed in the demo early on, is like it's a Unix style pipeline, right? First, we have some kind of boundary conditions, which is I want the ones that are. This is an example. The top one is what it would look like in Humio. Down here is what it could look like in a similar SQL thing, right? So we want the ones that are tagged with backend starting a day back, where the URL is something with conference 27. That could be this GOTO we're at here today. And then I want to group by the HTTP method and select the average response time. So you see the ideas are all borrowed from the relational model, but we kind of twisted it around to be a pipeline, but operate on the same concepts. So even though you can say we have our own programming language, our own query language, I think it embodies the concepts that we know from a relational world. It's very easy to get started with. So the way this runs then is that, as I said before, we don't do indexing. The way data is stored is in these segments, which are for each combination of tags. So this could be front-end tags, back-end tags, data center 1, data center 2, or service X or whatnot. Each combination of these creates a sequence of stored segments. And these are then just serial over time. They run a timeline. And each segment has the earliest log entry in the segment and the latest log entry in the segment. So we have a min and max for each of these. And that kind of index of the tags and the timestamps, we keep that in memory. And then when a query comes in, it could be I want to query the backend, the boundary conditions here. I want to query backend logs in time interval T1 to T3 that identifies these segment files. And then what we do is just basically just brute force our way through these in a very efficient manner. So each of these has a little time index. They have little blocks that we can decompress in chunks of the level 2 cache. So when we decompress them onto the CPU cores, that means we can run like a regular expression over the full log at blazing speed. So memory access on the CPU cache is much faster than had it been in main memory, for instance. The fact that it's compressed also adds to the effective I/O bandwidth, because we can just multiply the real I/O bandwidth by the compression ratio. So this actually works really, really nice, and it gives us a lot of flexibility. For instance, it could be that we want to run a regular expression. So here we take all these log entries, run a regular expression over them to extract a conference ID and do a group by conference ID. So maybe I should show this in a little example on the real data so you can see that this really works. So let's say instead of grouping by repo here, I want to run I take all the watch events, and then so a regular expression over this could be over the repository name. And the first part of the repository name here, that would be the owner. So let's say that if I extract just the owner part, oh, I lost my cursor. If I take just the owner part, let's say a named group like this. So these are the owners.
I think you put parentheses in the end. I think there might be one too much now when you lost focus.
One less. Here you go. So these are the owners of the repositories that got the most watch events, in this case, the last 5 minutes. Or we could actually run a regex like this over a longer period of time, and it actually runs really nice and fast over the last 24 hours here. So having the ability, if you have a setup where we do all this extraction up front, and you can only do it on ingest, you don't have the flexibility of extracting this. So with this, it's almost like a time machine. You can go back to logs that you pulled in a year ago and say, I wish I indexed that field and run regexes over this old data. Okay. So this is kind of just a summary. We have these Unix pipeline style. Many queries aggregate anyway, so this is kind of the argument why we don't really have index. And in many cases, you end up scanning lots of the data anyway. So Humio is really just super fast at doing table scans. It's a database optimized for doing table scans of sorts. So how do we get the speed? So this goes back to this notion of mechanical sympathy. So Jackie Stewart, he was this Formula One race car driver in the 60s. He won 3 Formula One race global championships in a row in the late 60s. And his idea and the meme that he came up with was this notion of mechanical sympathy. So to be a super race car driver, you need to understand your car. You need to be a mechanic. You need to be the car. You need to feel every corner of the car. and really understand how it behaves. So Martin Thompson has picked up this idea of mechanical sympathy and applied it to computers. And he's been doing the rounds of the major software development conferences like GOTO, and talking about cores and caches and memory controllers and CPU and I/O structures, etc., and how to optimize and how to write your programs to cater to this, how to be the CPU. You have to run really fast. You have to feel like you're sitting inside the CPU. I'm sitting on this core, and I can imagine what this memory feels like. It's right there. The local level 2 cache is right here. The other one is much slower to get to. And just imagine having this sympathy for being the computer. So this is what we've done. We've just done, the basics of what Martin has been telling us to do, which is, let me see, I just want to get back to me, which is to feel like the computer. And in this context, it's really interesting. He often mentions this quote. The most amazing achievement of the computer software industry is its continuing and staggering cancellation of gains made by the computer hardware industry. We've been so busy, especially the last 10 years, doing these huge distributed systems, adding overhead on doing clustering, and adding all kinds of overhead where really if you take the point of view that you want to get the most out of the hardware, you can do amazing things. You can really do amazing things. But today it seems like virtual machines at Amazon, regardless of their cost, are just thrown at problems because I guess the salaries of the developers is just the thing that decides, because if the developers can solve the problem with less time, then it doesn't matter how many computers they buy. But often, it adds up when the systems get big. So we've taken kind of the opposite approach and say, how much can we get out of a machine? We want raw speed. So it means, the active data set of our inner loop fits on cache. Don't do any allocations in the inner loop, because anytime you do allocations, it ends up touching global data structures. All of this is built in Scala, by the way. So actually getting out of the way of allocations is somewhat tricky, especially in Scala. It's so easy to allocate a closure somewhere, an anonymous function. We do bind to core, disable hyperthreads, because multiple hyperthreads, they just end up thrashing the same caches. The compressed storage and having a really efficient streaming decompression is important. Laying out and organizing the reads, the actual disk I/O, so that it becomes sequential reads when you have to touch the disk, is important. So there's nothing new in this. This is all just standard tricks in the book. So if you just apply all this, you can really get amazing performance out of a single machine with standard I/O. So it doesn't have to be a big system to perform well. Actually, a small system which is tightly engineered can easily run circles around the big enterprise systems. So on the data ingest side, how we get data in, we have various APIs. We have our own HTTP JSON API. We've implemented Elastic's APIs, so you can use Elastic's beats things and Elastic's logstash infrastructure to push data into Humio. We have some various firewall log binary formats supported, because it turns out one of the places where it's very expensive to use these by volume products, by volume log products, is something like firewalls, because you could just get boatloads of firewall data. So that could be an interesting market for us, something where there's sufficient volume of data. We support syslog, and we can easily add more specific things. So arriving data that comes in, is really processed quite minimally. We essentially just compress it and persist it in append-only files. You can imagine we can take a huge load of data in this. We get stored into these segments. So we don't do indexing or B-tables and sort it on disk, this kinds of things. And you can easily take a gigabyte per day per core on an ingest node. So that's on the easy side. You can comfortably do that kind of thing and still do queries on the system, etc. This won't load the system in any significant way. So data that comes in is in the ingest pipeline is we have possibility to set up a Kafka, which takes the data before we put it into the engine itself. Once it's in the engine, we can back it up, store it in a block store, a separate file system or S3. And then whenever it's all the way through the system, we ACK it through the queuing system. So that means Humio itself is not in the business of this keeping 3 copies of the data. That's actually pushed off to the outside infrastructure of the Humio core. So if something is amiss, we can always get a copy from the block store, which supposedly has 3 copies. Or if it didn't get there yet, it is in 3 copies in the queuing system on its way into Humio. So this is one of the things that adds to making Humio really simple and makes it reasonable that a 3-person team could build this in 9 months. So the next thing we're working on is being able to run queries across multiple nodes. So spanning out queries across multiple nodes. Right now, the product that we come out with today is just a single node. But as you can imagine, it's relatively simple to scale this. Of course, there's some things, but given that we don't have state across these, it's not that complicated. So the product today is a single node. We deliver it online or hosted as a Docker container. You can download it, run it on-premise, and we have a demo system, as I showed you, at humio.com. So before we close, this is like almost we'll switch back to this slide. Let me show you just the website, if you want to go play with it. So there's this nice website where we've brought XIs back to life with our owl on there. There's I can easily spend 5 minutes just there's full online documentation of HTTP, the HTTP API, how to define your own extractors, parsers. There's a nice little tutorial that explains everything around here. Then there is, if we go, let me say one more time. The live demo is actually a full system that just takes the GitHub activity stream, where there's some pre-baked queries you can try out and play with here. There's, for instance, it could be we want to take this one where we compare Docker versus Akka, and say, give me a time chart of this in spans of 4 hours. All right, so this shows the activity on Docker versus Akka. So you can run these pre-booked. I mean, there's nothing here that doesn't tell you that you couldn't write something else here. It could be Erlang OTP if you're an Erlang guy. See, it's kind of low. Anyway. So yeah, so it's this is really easy to just play with. The query I showed you the watch event grouped by repo name. These are the most watched, or the ones with the most stars on GitHub. We'll see here, the last hour, these ML algorithms won over the Palantir since we started, right? So it's easy to go in and look. You should just go type in your own repository names here. I'm sure there's not that much happening. Nothing really happened at Trifork the last hours, in terms of watch events at least. So, okay, I think we'll go back to just questions from here. Yes, if there are some questions that have come in, I don't know.
First, thank you for talk.
You're welcome.
Every goddamn time. Every time. We did get some questions. I'll try to do some aggregation of the questions because some are sort of overlapping. There's a question about the technology stack, and in the meantime you talked about Scala and Kafka, but it looks a bit like Kibana, so probably the technology from the web front end will be the question, what that is.
Oh, the web front end. Well, that's written in Elm, so it's all pretty much all Scala and Elm. So that's actually, we've been very happy with using Elm. It's I think we have like 45,000 lines of Elm for this. So it's a quite significant Elm project. That it goes well hand in hand with the Scala stuff. Yes.
Oh, that's one of the first production Elm systems I hear about, which is pretty cool. Next question, do you consider making it open source?
Well, anyone is welcome to just buy it and make it open source, I'd say. I mean, that's definitely an option. But yes, of course we've had lots of thoughts on the business model of this, and we've seen many of our friends, struggle making money off open source the last several years, the last 10 years, and so we decided we're going to try with a closed source model here. I mean, of course, there'll be open source components coming out to the side, and open source, the adapters and various things that are surrounding it. We're already starting to see some open source libraries that push data in from mobile phones and various places. So it's the beginnings of some of community like that is already starting to show up. But it's not going to be open source anytime soon, unfortunately.
What is the search engine behind Humio?
Well, the search engine behind Humio is Humio. That's the engine itself. I mean, we wrote that from scratch. So it's all, well, I have a lot of background in also, I've been working on React, on the React key value store. I've actually, in several rounds, spent 6 months on the core storage of that. I've written key value stores before that. So we have several people on the team who has experience in this. And this is very different in that it's not really a database as such. It's an orchestration of this brute force processing of logs. That the combination of having really relatively fast brute force and then having these standing queries that can answer instantaneously. We find that's a good balance. Of course, we have some really large, we're playing around with some really large-scale customers where going over a month of data is something that takes 10 minutes. And that's, of course, sometimes an issue. But the ability to take a massive amount of ingest is also a huge plus in many situations. Yeah.
I think you already answered part of that, but still here we go. Why is Humio better than other open source solutions like, for instance, the Elk stack? So what's the major advantage, I guess?
Well, Elk is good for some things, and I think we're good for some other things. So with Humio, we don't spend so much CPU when the data comes in. On the other hand, we assume when you run a query, we use all the CPU there is on the machines that run Humio. So we kind of shift the CPU usage to query time. And that means it doesn't work well if you don't want this to be exposed to 1 million customers, for instance. It's really nice for something where you use it for DevOps, for monitoring, where there's 10 users or 15 users that use it for querying. The upside then is you can run on much less hardware. So that's a trade-off. Elastic is very good at finding, the needle in the haystack. If you know something specific you're looking for, it has those indexes, and that's going to beat us every time, right? But in many cases, we found actually the way that most of our experience in production systems have been in running based on Splunk. And Splunk works more like this, where you just scan over time and have this flexibility of running regexes, and you have much more flexibility and interactivity. It's easy to formulate the queries in a human-readable language. So that's more what we try to do something in that end, and of course make it faster. But yeah, so we're different. It's in a different point in the set of trade-offs, and I'm sure every product has its hotspots where it's very, very good. I think this has the hotspot, which is what we would like to use. I think that's based on our experience.
Still got a couple of more questions to go. Why is Apache Spark and Apache Flink not the best fit for the processing part inside Humio?
Because with those technologies, you end up having to reify your data. You end up accessing your data out of main memory. If you want to control at this level that you're accessing data in this very controlled way and keep it on the CPU caches. What ends up happening in Humio is you can memory map data in, and you take a small chunk of that, decompress it onto level 2 cache, and it's just so, in a way that makes it an order of magnitude faster than having to allocate objects all the way. We don't even allocate an object for each log entry. So it's a memory mapped underlying structure, and we have a shared object that you run over and over again, just points to an offset, and we have our own string matching implementations that don't allocate memory in themselves, and there's just this total careful. So I'm certain we can run an order of magnitude faster, at least, and these systems that are somewhat similar in that they're MapReduce style systems, but they end up reifying and creating objects for many of these values as they flow through the system. So the downside is here, of course, that you can only do the things that are each of these optimized operators like filtering and group by, etc. do because they're optimized to run in this particular way and allocate as little as possible. Yeah.
And how does it work with petabytes of logs?
Slowly. So so we were working with one particular customer. We have a couple of. Obviously, the interesting aspect here is moving this into the really large systems, because if you can, instead of bloating your data by building indexes, you can shrink your data by compressing it on the way in. Then you can get maybe several orders of magnitudes of savings on just disks and computers that need to manage large amounts of data. So the bigger the data set we can push Humio onto, the more interesting it is, and the bigger an effect and the value we can create. So we do have two large customers, international large businesses in Denmark, where we have really large data sets and we're working with them in various ways. So hopefully, next year at GOTO Berlin, I can tell you more about those. But basically, it amounts to, doing some amount of scaling out for the processing, and also being able to shard the data in various intelligent ways. So that can speed up the queries. Yeah.
Okay, we're almost running out of time, so one last small question. How can I use this at my company? Is it already available? I think the answer is yes.
It is. Yes.
It is yes. So there were a couple of other questions, but can't tell them now because now the reception starts outside. We're over the time, but I think he'll be around. The whole team will be around at the stand, so you can talk to them. So just go out right and then continue the conversation. So thank you very much.
Thank you.